Section 10.1 talks about using the properties of tangent lines. So our first diagram here demonstrates the two pieces of a tangent line, one of them called the point of tangency, and that is where the tangent line actually intersects the circle, and then what we call a tangent line. Now a tangent line only intersects a circle at one point on the outer piece of the circumference, and that point that it intersects is called the point of tangency. One of the important concepts of the point of tangency together with the tangent line is that it makes a 90-degree angle with the radius that comes out from the center. So we see in this diagram down here that we have our radius, and then we have our tangent line, and where they intersect one another, that's going to be where our 90-degree or right angle is. So of course, if we're dealing with right angles, then we're dealing with right triangles. So there are a lot of things that we know about right triangles that we've studied all year, and one of them is going to be this idea of the Pythagorean theorem. We're actually going to start with our second example down here, and it says, if a line is perpendicular to the radius of a circle and crosses through the circle once, then it's a tangent line. So down here we're proving if line segment AB is or is not a tangent line, and if that were true, we would have a right angle and therefore a right triangle. Well, we know with right triangles, if they are right, they are going to fall into our category of Pythagorean theorem. So taking a look at our sides here, remembering that our right angle points to our hypotenuse here. The A and B sides, of course, are interchangeable. And then the C is going to be the hypotenuse. Taking our handy dandy calculator, and 7 squared plus 24 squared gives me 625. And 25 squared gives me 625. So because they are equal to each other, that means yes, it's a right triangle. So therefore AB is a tangent line. Going up to the first example on this slide is a little bit more difficult, and that's why they should probably be switched around. But if I take a look at this particular right triangle, it tells me that RT is tangent to the circle at the point of tangency R, and it says find the length of the radius. So this is going to require us to do some algebra. Both of those radii we don't know, so we're going to call both of those lengths x. So this length right here is x, and this length right here is x. Now, we'd like to run this through our Pythagorean theorem. So we would like to run it through our a squared plus b squared equals c squared. But it's going to be a little bit difficult. Taking a look at our c value, it's this entire part right here, which we would call x plus 7. It's what we call in algebra a binomial. So our a squared, we're just going to put in one of the legs, and then the b squared, we're going to put in the other leg. And the c squared is tricky because it is a binomial squared. Now we have to train ourselves with binomial squareds how to get rid of those parentheses. A lot of students want to do that wrong, so I want to make sure that you know how to do this correctly. So we're going to come over here, and we're going to build an area box, and we do that so we don't forget any part of our binomial. So we have x plus 7 times x plus 7, getting our area inside. Our x times x gives us x squared. X times 7 is 7x. 7 times x is 7x. and 7, 7 is our 49. So we're going to simplify down our equation to x squared plus 144 equals, and then if I come over here to my area box and I put together my like terms, I end up with 3 terms, which is called a trinomial. Now, at this point, we want to solve it for x, so we'd like to get our x's to one side. Well, if we try to move our x squareds around, we notice that if we subtract off our x squareds, they actually eliminate on both sides of our equation. And then our equation simplifies down to something that's much more simple. And then we just solve it using our algebra skills. 144, subtract off 49 from each side, gives me 95. Divide both sides by 14, and I end up with approximately 6.8. So the radius for that particular circle is approximately 6.8. One of the other concepts about tangent lines is that if we have two segments and they're both tangent to the same circle, that means that those tangent lines are congruent to one another. So in other words, these two lengths are going to be equal. We have 2 more vocab words down here. So we've got an inscribed. So an inscribed polygon sounds like it should. So it sounds like inside, and that's exactly what it means. It's a polygon that's on the inside of a circle. And then the opposite of that is going to be called circumscribed. So that gives us a whole bunch of tangent lines out here that only touch our circle at one point. Got a little excess there. So there we have an inscribed pentagon and a circumscribed pentagon. Now, if we take those two particular pieces of information and we put them together, and we take this figure up here on the top, and we use that idea of tangent lines that intersect the same circle are going to be congruent to each other, and that we have here a circumscribed polygon, we should be able to find the perimeter of that particular polygon. Let's see, how many sides does it have? 1, 2, 3, 4, 5, 6. That's a hexagon. Okay. So we're going to come through here and we're going to figure out some of our pieces. So if we start up here with this 9, if we've got this tangent line right here is 9, then we know that this one right here is also 9. If we've got this length right here is 10, then we know this length right here is 10. Okay. We keep going. Here's 15. So we've got 15 and 15. Down here we have 12. And then the center to this part, so this tangent line right here would also be 12, making this side over here 12. No, sorry, we've got 8 left over on this side. And then of course we would have 8 for this particular tangent. And then what's left over from the 18 would be 10, which gives us this missing piece right here is also 10. So just our powers of deduction to get all those to come together. And then we just go ahead and use some calculator power and we just add those all together. And we end up with a perimeter of 101 units. The next figure is all the different pieces that you're going to find of lines that are going to cross through a circle. So there's a couple of these that are very familiar to us that we've worked with since we were in elementary school. So we've got this one right here, which is our radius. And we've got this one right here, which is our diameter. And before you took high school geometry, those were the only two pieces of a circle that you really knew about. But there are three other lines within a circle that have names that have special characteristics of them that we're going to study. So this one on the outside is what we've been talking about today. So this is our tangent line. And then inside here, we have this segment right here, which you notice that it ends on each part. The end points are on the circle itself, but it doesn't go through the center. So that is referred to as a chord. And then our last line up here that goes through the circle, so notice that there's arrows on each end of that. It goes through the circle, but it doesn't cross through the center. That is called a secant line. Doing a little bit of algebra with what we've just learned. So this has to do with some of the angles. This particular polygon, some of it is on the inside and some of it is on the outside. If we remember back to our previous chapter when we talked about properties of quadrilaterals, this quadrilateral is going to be a kite. But because those two lines right there, we're going to assume someplace in the directions that it tells us that those are going to be tangent lines, we're going to assume that those are both 90-degree angles. So, because we have a quadrilateral, we know that the interior angles add up to, let's see here, there's two different ways to do it, but a lot of times we use this formula. And minus 2 gives me the number of triangles, and then times 180. Well, let's see, we've got 4 sides, right? And that's going to give us, of course, 2 triangles. So 2 times 180 gives me interior angles that add up to 360. So if I take this particular quadrilateral kite, and we add up all of our angles, our interior angles, x plus 90 and 90 and 152 should give me 360. And then we just go ahead and use our algebra skills, add up all of our like terms here, and we get x plus 332 equals 360. Subtract off our 332 from each side, and we get that that lower angle there, the x, is going to be 28 degrees. And one more slide. The purpose of this last slide is just to show you what common tangent lines could look like. So it's 2 circles that share a tangent line, and there are a number of different ways that that could look. So our first one up here on the upper left, you can see that the tangent lines come on the outside of both of the circles, and we just touch on the outer point of the large circle and the outer point of the small circle. Upper right is going to show you another way to get 2 circles with a common tangent line. So we've got our small circle inside, our large circle outside. Notice that the inner circle is inside of the larger circle. So the small circle is inside the big one, and the tangent line just comes out, and there's just one of them. So Right, the first example had two tangent lines, two common tangents. Second one just had one common tangent. And then we get creative with a few more. So this next example right here, which kind of looks like a ladybug, it has three common tangents. This one has one common tangent. And this crazy mess down here has four common tangents. And that just gives you an idea of what a common tangent is and what they could look like as they're applied to each one of those different situations.